we are now going to solve this problem using related rates. So let's spend a minute or so to read the description, the wording description of the problem here. So a street light is at the top of a 15 feet tall pole. A woman 6 feet tall walks away from the pole with a speed of 4 feet per second along a straight path. So how fast is the tip of her shadow moving when she is 30 feet from the base of the pole? Okay. And so let's now extract out information and try to make a sketch here. I have a high recommendation for anyone that anytime we're doing these problems where we need to apply related rates, then draw a sketch would be a big help into our work with that. So now first let me get to a sketch, and then from the sketch we will be able to identify our variables. So a street light is at the top of a 15 feet tall pole, and there's a woman 6 feet tall. It's basically woman or man, it's a human being walking away from the pole, and the person is 6 feet tall. So with that, let me get back on the board and try to do some sketching description here of that. So we have here is the ground. So the light pole is of course it's a pole 15 feet up the ground right there. So the light is here, the street light is here, and so the 6 feet tall human being is here. Okay, so forgive me that I cannot do the best drawing here, but now it is known from physics that when any light casts a shadow through a person like that, right? Basically there's another height, lower height than this light right here. Then if there's a light ray that casts a shadow, then it goes through the tip of the person of that lower height right here and hits the ground. And so the shadow is, this is the shadow from where the person stands. Okay, that's the shadow right there. But I am not going to rush into naming the length of the shadow yet. But you can see that the idea now is that as she walks further out, as the person walks further away from the pole right here, then that shadow gets longer. So this is her tip of the shadow. Okay, and then of course this distance from the pole right here is where she stands away from the pole. And as according to the way how the problem is describing, she's walking away from the pole. So now we already knew that the pole is 15 feet tall. The person herself, the person here is 6 feet tall. Okay, and of course the way how it is, any pole is standing straight up vertical with the ground. So we have a right triangle right there. And the same way how we stand, any person when we stand vertically from the ground. So there's a right angle there again. So basically the setup we have here in the sketch is a situation of a big right triangle with another one smaller than that, but being another right triangle as well. So these two triangles, there's one of them being smaller scale and the other one is being larger scale. These two are similar triangles. So as I'm mentioning it now, I highly recommend that any one of my viewers here to go ahead and pause the video if you need to review your past understanding about similar triangles before we can move on right here. But in any two similar triangles, let's say the smaller one here and the bigger ones, then we have this edge here and that edge there are being considered as corresponding edges or corresponding sides. This lower side, this shorter side here on my smaller triangle is corresponding with this longer side right here, but then correspond with that side on the bigger triangle. So anytime the thing I need to remind anyone about similar triangles is that they will always have pairs of corresponding sides. Okay, and then so go ahead and review your understanding on the similar triangles. All right, so now hopefully you have had some review of your understanding in similar triangles. And so now here's what I'm seeing. First of all, let's name the variables a little bit. So I'm going to call the distance from where the woman stands to the base here, or in other words, her position from the base. I'm going to call that S. Okay, I'm going to call that S. And then I have my reason, and I will explain that later. But the total distance from where her tip of her shadow, from where the tip of her shadow is, back to the pole, that's total distance right there. Again, from the tip of her shadow back to the base of the pole. That distance, how about we can call that x? Okay, and so it makes sense perfectly that the length of her shadow, is always casting out from where she stands, from where her base is, out to the tip of the shadow. But that length there is only the total length from where the tip to the of the shadow to the base minus s. Okay, so that hopefully is clear enough in the picture. So now I reminded about the concept of similar triangle because so here's the thing, as anywhere she stands, at any instance where she stands, then we have, as I already said, we have a similar triangles situation. And so as far as corresponding sides, this length x minus s right here, x minus s, okay, is corresponding with the entire length x. So I'm going to say x minus s over x as a ratio. The rule of similar triangles guarantee that once you set up a ratio here, that ratio should be the same for the rest of the other corresponding pairs of length. So on the other corresponding pair of length here, we're looking at 6 feet. The woman's the height is being in ratio with the light pole's ratio. So that ratio should be equals with x minus s over x. So 6 over 15 is equal ratio with x minus s over x. So we have a ratio constraint right here. Okay, and so now, but from this, we actually brought for ourselves an equation. So here's the thing. Go ahead and reduce this fraction here, 6 over 15. I can quickly erase this and turn that into a 3 out of 5. But now, at this point, strictly staying on the algebra, then we can cross multiply the 5 here is to multiply with the other opposite side, and x here is multiplied with 3. And so we can turn our equation into 5 times x minus s equals 3x. So I just simply did a cross multiplication, as everybody has already knew. Okay, cross multiplication that way. And now I can go ahead and also multiply that 5 to each term on my left-hand side. So I'm looking at 5x minus 5s, okay, and to equal 3x. Okay, and so now from this equation, I am going to move one more step right here. I am going to bring so at least we have some like terms throughout the two sides of the equation. So I am going to bring that x term to the other side and bring the 5s term to my right-hand side. So that means I'm going to produce 2x equals 5s. Okay, so I have 2x equals 5s. Okay, so now this equation for us here is important. I'm not saying anything about the derivative yet, but this equation for us here is important. Okay, because it relates the two variables, the two main variables here, x and s. X and s. X is actually, I use x here as the variable representing the total distance from where the tip of the woman's shadow back to the base of the pole. That's x. So my relationship here is saying that 2x equals 5s. S is the position of the woman back to the pole. Okay, so it's all about the position. Either one of them is the position of where the tip of the shadow is to the pole, and the other one is the position of where the woman's base, the person's base to the pole. Okay, and so I have now a relationship relating the two variables here. Okay, and so now, once we recognize the relationship, I am going to head back to the wording on the problem a little bit more, and let's shop for good information here. So now we have already nailed down all of these information. The 15 feet tall pole, we already had that on a sketch. The woman's being 6 feet tall, we already had that on a sketch. So now this next piece of information right here is important for us. The woman, right, walks away from the pole with a speed of 4 feet per second. She walks away, okay, with a speed 4 feet per second. Walks away at that speed. That means, according to this picture, walks away. She walks away. So as she walks away, then that length S right here, or her position, gets bigger and bigger. Or she got more distance away. She got more positions away from this light pole right here. And so that speed was given there, 4 feet per second. So now I'm going to nail down the first piece of information right here. 4 feet per second. But that is how fast she's moving away. So that means we're looking at a rate of change ds dt. Because that's the change in her position away from the pole over time. And the reason I know now that it's dt, it's over time, because look right at the units that was given to us right here. The rate of change given is being expressed in terms of distance or position, change in positions over seconds. Time, it's a unit of time. That's how I know this rate of change is a rate of change in respect to time, the t variable, assuming that I'm using t as the time variable. Okay, so now we have, and of course, in our understanding at this point, any rate of change here is, of course, an instantaneous rate of change, or in other words, a derivative value. So we already had a given derivative value being the ds dt to equal 4 feet per second. And that also helped us to decide that any of our rate of change is in terms of t. And that's also another critical point that I need to mention right here. We now we decide that from this equation we will go ahead and differentiate in terms of t, because it's from right here we already had our rate of change being expressed in terms of t. Okay, so I'm sure there will be more other given information, but we will dive back into that after I found my related rates here from this equation. So now I am going to move to my other board. So 2x equals 5s. Now once we're clear that we need to differentiate both sides in respect to t in terms of t, and now we know that t is our main variable, but it's nowhere found in our beginning equation. Nowhere found in our beginning equation. That means any one of these is a function of t, and I have mentioned this so many times throughout the general lecture. And so now in this way, x is a function of t, but implicitly defined. S is another function of t, implicitly defined. And so the only way we can do finding these derivative in terms of t, I'm leaving that as a 2, because 2 is a coefficient. 2 times dx dt. That's about the best we can do. And so that equals, on the right hand side, I'm looking at 5 times ds dt. Okay. And so now, at this point right here, our equation that we just arrived here is another important point. It points out the relationship between our two rates. And that's why, once again, this is how we are saying that we apply our understanding of related rates. This equation here relates our two rates together. So we have two rates, the dx dt and the ds dt here. They're related by this equation. 2 times of dx dt is related with 5 times of ds dt. Okay, and so now, back on my other board right there, then we already learned from the wording of the problem that we had the ds dt given to be 4 feet per second. And so now that information will be useful in our work here. So ds dt now eventually we will substitute 4 into that. But now let's look back at the problem a little more. Okay, and so the question is looking for how fast is the tip of her shadow moving when she is 30 feet away from the pole. But really, let me just focus right now on this. How fast is the tip of her shadow moving? Okay, so how fast is the tip of her shadow moving? And that how fast right there is, in other words, the dx dt right here. Because in my picture that I have described, I define my x variable as the distance from where the tip of her shadow is away from the base of the pole right here. So how fast her tip of the shadow is moving, that means how fast, but how do we reference that? How fast based on the difference that based on the distance, that reference from where the tip is back to the base. Okay, that's how I define that. And so that means we're looking for d dx dt. So really, as our goal right here in this problem, we find to keep in mind, to nail it down right here, we find d dx dt. Okay, I'm organizing the problem a little bit different with the way how many other instructors are organizing it, but I want people to focus on the skill. I want my viewers, my students to focus on the skill of being able to get the related rates. And once we get that, and we're going to start identifying our goal, what to do with this related rates, as far as also nailing down what are being given in this related rates right here. And so now recall for yourself from the earlier board, from the other board, that we have the SDT given to be 4 feet per second. Okay, and so now everything is ready. So we know that we want to find dx dt, and we have an equation relating our two rates right here. And so now I'm looking at 2 times dx dt, that's what we are finding out, to equal 5 times 4. I got 4 here substituted for dx dt simply because we have our dx dt given from the problem, being 4 feet per second. Okay, and so now from this point, solving for dx dt is just a matter of, it's a product here between 2 and dx dt. Okay, so to solve for dx dt, we just simply divide both sides by 2. And so consequently, our final rate of change for dx dt is calculated by 5 times 4 divided by 2 right there. And that gives me final dx dt equals 10 feet per second. So the tip of her shadow. Now, so as long as the woman is walking at this constant given speed right here and walking away from the pole right here, 4 feet per every second, then her shadow is moving. I mean, of course, moving away in reference to the base of that pole right here. That she's moving away. I mean, the tip of her shadow is moving away in the same direction at 10 feet per second, a constant rate of change there. Okay, 10 feet per second, and that is how we solve. That is how we applied related rates, our understanding of related rates in solving this example over there.